Hello everyone and welcome back to another video. Today we're going to talk about the AN3 Exponent laws outcome. The main focus in this outcome will be talking about understanding powers with an integral exponent, which talks about positive and negative whole number exponents, as well as rational exponents, which means any exponents in the form of a over b, otherwise known as a fraction. Most of the exponent laws that we're going to explore in this outcome stem back to grade 9, so that includes your product of powers law, quotient of powers, power of a power, along with your zero exponent law. So those were all found back in grade 9. Now when we look at the new stuff for grade 10, we're going to talk about powers with negative exponents, as well as radicals and rational exponents. So before we get started, let's go ahead and define some key terms that will help us out in this outcome. First off, let's talk about what a power is. So we can define a power as an expression that represents repeated multiplication. So there's a few things that will help us out in this case. So this entire thing here, 3 to the power of 5, is what our power would be. And there's going to be two main parts of a power. The first part will be our base. This is what's going to be multiplied by itself a number of times. So in this case, this is going to be a 3. And then there's also what we call the exponent, in this case, a 5, which tells us how many times the 3 is going to be multiplied by itself. So if we were to simplify this or expand it, we can actually write this as 3 times 3 times 3 times 3 times 3, 5 times. So 3 to the power of 5 can be expressed as 3 times 3 times 3 times 3 times 3. Using powers is really just a really quick way for us to express the same thing without writing the same thing over and over again. So our first law is the product of powers. Essentially, if we have x to the power of m times x to the power of n, what we're going to do is we are going to add our exponents together. Putting this into practice, let's say we have 4 squared times 4 to the power of 3. This would be 4 to the power of 2 plus 3, which ends up being 4 to the power of 5. So why does this work out? Well, this expression, 4 squared times 4 cubed, is really the same thing as 4 times 4 times 4 times 4 times 4. And if we were to take these out of the brackets, because again, with multiplication, the order doesn't really matter, I can rewrite it as 4 times 4 times 4 times 4 times 4, which means that I have 4 multiplied by itself 5 times, which would, again, lead us back to our original answer of 4 to the power of 5. The second exponent law that we're going to review is our quotient of powers law. And all it states is that when we divide two powers with the same base, so if we have x to the power of m divided by x to the power of n, we are simply going to subtract those exponents. So for example, if I have 2 to the power of 4 divided by 2 to the power of 1, we simply take the exponents and we subtract them, and we end up with 2 to the power of 3. So where does this law come from? Essentially, we can rewrite 2 to the power of 4 as 2 times 2 times 2 times 2 divided by 2. What we can do here is one of two things. I can get rid of a common factor from both the bottom and the top of this fraction, which means that we're really just left with 2 to the power of 3 over 1, which is really just 2 cubed, and that's exactly what we want. So that is one way of having the same result. Or method number 2, and let's go ahead and label this one. Number 2, we can think of 2 to the power of 4 over 2 to the power of 1, again, as this right here. And I can actually rewrite this fraction as 2 over 2 times 2 times 2 times 2. Well, what's 2 divided by 2? Well, 2 divided by 2 is really just 1. And now I have 1 times 2 cubed gives me 2 cubed. So using either one of these two visualizations should hopefully help you see how this law can help us reduce the amount of work that we would need to do. Our next law that we're going to review is the power of a power law. Essentially, this just states that if I take a power and I have, for example, x to the power of m, and I raise it to the power of n, I am going to actually multiply them, m times n. Let's go ahead and try out an example. X to the power of 3 raised to the power of 2. This would mean that I take 3 and I multiply with 2 to give me x to the power of 6. But hold on, wait a minute. How did this happen? Well, let's think about what's going on here. We're taking x cubed and we're squaring that. So if I were to rewrite this, x cubed, and I'm squaring it, I can rewrite this as x cubed times x cubed. Now hopefully this looks kind of familiar. This actually just goes back to our first power law, which is the product law. Since we are multiplying two powers with the same base, we now need to add our exponents. So we're going to add 3 plus 3, which gives me x to the power of 6. I'm going to go ahead and use another example here. This is one that I typically see students making a lot of mistakes on. So let's say we have something such as 3x to the power of 4, and we're going to raise this to the power of 2. Now, according to the power of a power law, we need to apply this exponent. We need to multiply my exponents on the inside with the exponent on the outside. Now, this is actually easier said than done. If I were to ask you, what are my exponents of everything inside of here? Most students would only look at the 4 and say, well, we're just going to multiply the 4 and the 2 together, which is correct. We would end up with x to the power of 8. But what a lot of students forget is that this 3 is actually to the power of 1. So now we have to multiply 1 times 2, which gives me 3 to the power of 2. So this is a very important step that a lot of students forget. So 3 squared gives me 9, and I would have 9x to the power of 8. So you might ask again, well, how does that work out? Why does this work? Well, let's examine our example again. 3x to the power of 4, when we square it, is really the same thing as 3x to the power of 4 times 3x to the power of 4. What we need to keep in mind is that we're going to multiply our numerical coefficients together. So I have 3 times 3 gives me 9. I have x to the power of 4 times x to the power of 4. And using our power of a product law, that would give me x to the power of 8, which is exactly what we wanted. Our next exponent law that we're going to review is the zero exponent law. And all it is that x to the power of 0 is equal to 1. That's it. There's no trick to it. Well, how does this law work out? Let's say we have 3 to the power of 2 divided by 3 to the power of 2. According to the quotient of powers law, this would be the same thing as 3 to the power of 2 minus 2, which is 3 to the power of 0. So once we get this established, let's go ahead and rewrite the exact same thing. 3 squared over 3 squared. We know that 3 squared is 9, divided by 3 squared is also 9. So 9 divided by 9 is really just equal to 1. Well, since we started off in the same place, that must mean that 3 to the power of 0 has to be equal to 1. Let's go ahead and talk about our first new exponent law of grade 10, which is our negative exponent law. All it states is that, for example, if I have x to the power of negative m, this is really just the same thing as 1 over x to the power of positive m. So how do we go about proving that this is an actual law and not just something that I've made up? Let's take a look at an example. I'm going to take 2 to the power of 0 and I'm going to divide it by 2 to the power of 2. According to our quotient law, I'm going to subtract my exponents, which gives me 2 to the power of negative 2. I'm going to go ahead and rewrite the exact same thing underneath. But now I'm going to look at my zero exponent law that we just spoke about. 2 to the power of 0 is just 1 divided by 2 to the power of 2. Well, since we started off with the exact same thing, this implies that these two results must equal the exact same thing. So 2 to the power of negative 2 is the same thing as 2 to the power of positive 2, which is exactly what we have here at the beginning. If you're struggling with that, let's go ahead and use another example to help us out. 3 to the power of 2 divided by 3 to the power of 3. This is really just 3 to the power of 2 minus 3 if we use our quotient law. So this means that we have 3 to the power of negative 1. Using the exact same starting place, we have 3 squared over 3 to the power of 3. We could actually rewrite this as 3 times 3 divided by 3 times 3 times 3. And now we can start getting rid of common factors from both the top. And now we can start getting rid of common factors from both the top and the bottom of this fraction. Remember that we just have a 1 left on top and we have a single 3 left on the bottom, which coincidentally gives me 3 to the power of 1. So since we started off in the same place, that means that our results from here must be equivalent. So 3 to the power of negative 1 is the same thing as 3 to the power of positive 1, which is exactly what we wanted. So using our newly minted negative exponent law, let's go ahead and simplify these by turning these into powers with positive exponents. Since I have 6 to the power of negative 6, I'm going to rewrite this as 1 over 6 to the power of 6. Using my trusty calculator, I know that 6 to the power of 6 is 46,656. So my final answer is 1 over 46,656. 2 to the power of negative 1 is really just the same thing as 1 over 2 to the power of 1, which is just 1/2. Before I move on to the last example on this page, I want to show you a little visual cue that I typically tell my students. For example, if we are looking at 3 to the power of negative 2, I actually tell my students to rewrite this as 3 to the power of negative 2 over 1. So make sure everything starts off as a fraction. Because I have a negative exponent on top, I want to think of this as being in the wrong spot. So since it's on top, I'm going to move the entire power down to the bottom and make this a positive 2. When I move something off the top, it's just going to be a 1 left in its place, which is exactly what we wanted. You might be wondering, well, why does this work? Why am I allowed to do that? Well, let's go ahead and re-examine the question. 3 to the power of negative 2 can indeed be written as 3 to the power of negative 2 over 1. What we want to realize is if I were to rewrite this using your negative exponent law, this would be 1 over 3 squared divided by 1 over 1. Since we are dividing two fractions, I'm going to take my top fraction here in my numerator, so 1 over 3 squared, and I multiply it by the reciprocal of the bottom fraction. So the reciprocal of 1 over 1 is just 1 over 1. This leaves me with the exact same result, 1 over 3 squared. So this isn't necessarily a trick, but more of a visual cue. Once again, if you see a negative exponent up top, you can move the power that it's associated with down to the bottom. So this last problem can be solved in one of two ways. Let's go ahead and do it the long way first. Since we're going to apply that negative power to both the 4 and the 5, let's go and do that first. 4 to the power of negative 3 over 5 to the power of negative 3. This would be the same thing as 1 over 4 cubed divided by 1 over 5 cubed. Since we're dividing two fractions, I'm going to take my top fraction here, and I'm going to multiply it by the reciprocal of my bottom fraction. So I'm going to switch my numerator and denominator, so the 5 cubed goes up top, and my 1 goes on the bottom. Since we are now multiplying fractions, I multiply across the top, which gives me 5 cubed, and I multiply across the bottom, which gives me 4 cubed. And we can go ahead and simplify this as 125 over 64. So that seemed kind of tedious, wasn't it? So this is really just the long way of doing a question like this. Here's a bit of a shortcut. Now you might want to use this second method with some caution, as your teacher may or may not want you to show a little bit more work and how you ended up where you are. So if we know that we're dealing with some sort of fraction inside of the brackets and we have a negative exponent on the outside, all I'm going to do is I'm going to actually flip my numerator and my denominator. I'm going to take that negative and turn it into a positive. Now, before I explain why you're allowed to do that, let's go ahead and finish the question. I'm going to distribute this 3 to my exponents. So I know I have 1 times 3 and 1 times 3. So I have 5 to the power of 3 over 4 to the power of 3. And now already within 2 steps, I am in the exact same spot as I was down here at the bottom. And I can go ahead and simplify this as 125 over 64. Now hold up, wait a minute. Why are we allowed to do that? For those of you who just want to have the shortcut, know the shortcut and use it, feel free to skip ahead. But for those of you who are a little bit more curious, here's why. If we think back to our negative exponent law, I can actually rewrite this expression as 1 over 4 over 5 to the power of positive 3. I can then go ahead and distribute that 3 to both the 4 and the 5, which leaves me with 1 over 4 cubed over 5 cubed. I'm going to rewrite this one as 1 over 1, and then once again 4 cubed over 5 cubed on the bottom. And from here, I'm going to multiply by the reciprocal of the bottom fraction since we are dividing 2 fractions. So I have 1 over 1 times the reciprocal of this, which means I'm going to flip the 5 cubed and the 4 cubed. So I have 5 cubed over 4 cubed. And since we're multiplying fractions, I multiply across the top, divided by 1 times 4 cubed, which is just 4 cubed. And that's exactly what we wanted. So hopefully this explains why you're allowed to use said shortcut, but really we're just skipping a couple of steps in terms of showing all of our work. So like I said before, use caution in case your teacher does want you to show some sort of intermediary step. Otherwise, this is a quick way to cut down on the amount of work that you have to do. So before I go ahead and introduce the rational exponent law, I would like for you to use your calculator to evaluate these following expressions. Hopefully we were all able to arrive at the same answers. So 9 to the power of 1/2 is just 3. We know that the square root of 9 is 3. 64 to the power of 1/3 is 4. The cube root of 64 is 4. 625 to the power of 1/4 is 5. And the 4th root of 625 is also 5. So what do we notice here? Well, if you guys look carefully, you'll notice that the top expression is an exact match with the expression directly below it. 9 to the power of 1/2 is the same thing as the square root of 9. 64 to the power of 1/3 is the same thing as the cube root of 64. And 625 to the power of 1/4 is the same thing as the 4th root of 625. If we take a closer look here, we'll notice that this 2 is really just our hidden index of our square root. So again, remember that we do not write the 2 if we are taking a square root. So I'm going to go ahead and erase that. This 3 here happens to be the same thing as our index of a cube root. And the 4 here is the same thing as our index here for this 4th root. That's correct. The denominator of the exponent is the index of the corresponding radical. So in general, if I have a to the power of 1 over n when n is greater than 0, this would be the same thing as the nth root of a. So once again, we're going to take note that the denominator of your exponent is the index of the radical that results. So if we take a look at a couple of examples here, since the 2 is our denominator here, we are going to be taking a square root. And we're going to take a square root of our base, so the square root of 16 is equal to 4. In our second example, our denominator of our exponent is a 3, which means that we'll be taking the cube root of our base, so the cube root of 8 is just 2. So this last example actually appears a little bit further on in our notes, but I'll go ahead and explain it now. What I want to think of this as is 16 to the power of 3, but I also want to consider this as 16 to the power of 1/4. Since our denominator of our exponent is 4, That means I'll be taking the fourth root of our base, so 16. But because we also want to think of this as 16 to the power of 3, we need to also keep this in mind. So we'd have 16 to the power of 3, but we take the fourth root. So the fourth root of 16 cubed is what we would end up with. We'll find out later on that it's actually a little bit more practical to think of this as the fourth root of 16 and we are going to cube the result. So both of these are actually equivalent, but we'll talk about this a little bit more in depth later on. Let's go ahead and work through a couple of examples. Since we have the same base and we're multiplying powers, we're going to subtract our exponents. So this would be 0.3 to the power of -3 plus 5. And -3 plus 5 gives me 0.3 to the power of 2. This second example looks a little intimidating, but we're just going to break this down into steps. I'm going to go ahead and simplify each of these power of a powers first. So that means we're going to take the -4 times 2. That will give me a -8. So over here on the left, I'll have -3 over 2 raised to the power of -8. And then over on the right hand side, I'll have 2 times 3, which means that I have -3 over 2 to the power of 6. Now, since I'm multiplying powers with the same base, the base is -3 over 2, I'm going to add my two exponents. So -8 plus 6 gives me a result of -3 over 2 raised to the power of -2. Using my little trick from a few slides back, because I know I'm working with a fraction here inside of the brackets and a negative exponent on the outside, I can rewrite this by flipping the top and the bottom, my numerator and denominator. So I'm going to have -2/3 on the inside, and this will now be raised to the power of 2. So technically we're done here because we have written this as a single power. We can actually go ahead and simplify this a little bit more. We can think of this as -2/3 times -2/3, which in the end gives me a positive 4/9. In example C, there's a couple different things we could do. I'm going to go ahead and simplify the top here first. Since we are multiplying powers with the same base, I'm going to add the exponents, which means that I have 1.4 to the power of 7. And now we're going to divide it by 1.4 to the power of -2. Well, since we're dividing two powers with the same base, I'm going to subtract my exponents. So this means that I have 1.4 to the power of 7 minus a -2. Keep in mind that when we subtract a negative number, this will mean that we are adding them. So this means that we have 7 plus 2, which means I have 1.4 to the power of 9. In this last example, I see a lot of students make the mistake of trying to simplify things way too early. Remember, in terms of BEDMAS, we want to try to figure out and simplify everything inside of the brackets first. So we're going to go ahead and do that. Taking a look at the bottom, I'm going to keep the top just the same for now. We have 1/3 and 5/3. Since we're multiplying powers with the same base, I'm going to go ahead and add them together. 1/3 plus 5/3 gives me 6/3. We are still raising this to the power of 6 in the end. So let's go and simplify what we have on the inside. So we're going to take 2/3 and we're going to subtract 6/3, which means that we're left with 7 to the power of -4/3 on the inside. We're still raising it to the power of 6. Since we have a power raised to a power, we need to multiply them. -4/3 times 6, or 6/1, means that we would end up with -24/3, and -24/3 is the same thing as -8. So that would mean that my final simplified form is 7 to the power of -8, but most of the time your teacher will want you to write this with a positive exponent, which means that I will write this as 1/7 to the power of 8. Taking a look at a few more examples here, we have x cubed y squared times x squared y to the power of -4. The thing to keep in mind here is that everything that's happening in between the variables is really just multiplication. We have a multiplication sign there that we don't see, one there and one here. The nice thing about multiplication is that it means the matter doesn't really order, so I can reorder this whichever way I want. Well, I want to think of my x's being right beside each other. I am multiplying them. So since we're multiplying powers at the same base, I'm going to go ahead and add the 3 and the 2 together, which gives me x to the power of 5. I'm going to add the 2 and the negative 4 together, which gives me y to the power of negative 2. Now, once again, using that visual cue that we discussed earlier, I'm going to place this over 1. What this does is it allows me to identify, okay, my positive exponents will keep my power up top, but since this is a y to the power of negative 2, it's in the wrong spot. So I'm going to go ahead, move it to the bottom, and turn that into a positive exponent. Alternatively, what you could also think of this as, if we have x to the power of 5, y to the power of negative 2, this is really just the same thing as x to the power of 5 times 1 over y squared. If we think of this x to the power of 5 as a fraction, we have x to the power of 5 over 1. And since we're now multiplying fractions, I multiply across the top and multiply across the bottom, giving us the exact same thing. So typically this next example is the first sign of students running into a little bit of trouble and over applying exponent laws. When we look at the coefficients of 10 and 2, we tend to forget that we're now just dividing two numbers. The exponents are the same. This would be 10 to the power of 1 divided by 2 to the power of 1, but they are not the same base. So we can't treat them the same as if they had the same base. So all we need to do is take 10 divided by 2 and gives me a 5. Over here, I've got a to the power of 5 over a to the power of 2. So I've got a to the power of 3 since we're subtracting 5 minus 2. Last but not least, I'm going to take the b cubed and the b to the power of negative 2. I'm going to subtract 3 minus a negative 2. So that's really the same thing as 3 plus 2. And I end up with b to the power of 5. So on this page here, you guys can go ahead and pause, try out the examples, and then unpause once you're completed. So I wanted to pause and take a minute to talk about these last few examples here. Negative 6 to the power of 0 when it's inside of the brackets is really just the same thing as negative 6 divided by negative 6, which just gives us a 1. So that's pretty straightforward. Now the answer to the second one here is going to actually be negative 1. Now the reason why this happens is that BEDMAS would actually treat this like this, negative 1 times 6 to the power of 0. Well, this would be negative 1 times 1, which gives me negative 1. The last example on this page is a little bit tricky as well. This is really just the same thing as 3 times x to the power of 0. And we know that x to the power of 0 is just 1, which means that my final answer is 3 times 1. Once again, feel free to pause, try out these questions, and then unpause once you're finished. I want to take a second and talk about this question here. Remember earlier when I took an example such as x to the power of negative 2, I said to think of this as being x to the power of negative 2 over 1. This negative exponent implies that the whole power is in the wrong spot, so we're going to have our fraction again, and we're going to move that whole power to the bottom and make that exponent a positive number, leaving a 1 up top. What would happen if we have a negative exponent in our denominator, or otherwise known as the bottom of the fraction? Well, it's going to be the exact same thing except flipped. This negative exponent in the bottom of the fraction implies that this is in the wrong spot, and we're now going to move it up top and make it positive. A 1 stays on the bottom, but really 4 cubed over 1 is just 4 cubed. And we can simplify that as 64. For the example that I just did here, notice that the -7 stays up top. Why does it stay up top? Well, if we think about the exponent of that -7, it's really just 1. This -2 only applies to the x. So make sure that you're not accidentally taking too many things over to the other side. So taking a look at the last 2 questions here, I'm actually going to go ahead and draw my line for a fraction first. The reason I do this is so that I can keep track of what variables are going to stay on the top or the bottom. So looking at my coefficients, I've got 16 divided by -4, just leaves me with a -4. A to the power of 6 divided by a to the power of 6 leaves me with a to the power of 0, which is just 1, so I don't need anything new there. Then I have b to the power of -3 over b to the power of 3. There's a couple ways I can think about this question. I can go ahead and subtract my exponents. -3 minus 3 gives me b to the power of -6. So now I can pretend that this whole thing is divided by 1. And now since I know I have my b to the power of -6, it is in the wrong spot, so I'm going to move it down to the bottom, and it becomes b to the power of 6. The -4 just stays up top. The last question on this page is also a little bit tricky. Since this whole bracket is to the power of -2, I'm actually going to go ahead and move that entire thing down into the denominator. So what that's going to look like is I'll go ahead and draw my line for a fraction. I'll have 1 up top. I'll have that 5q4 on the bottom. But now that 5p is raised to the power of 2 on the bottom. So we'll go ahead and simplify. I'm going to distribute this 2 to both the 5 and the p. So we are left with 1 over 5q4, 5 squared, p squared. And if I go ahead and simplify everything, 5 times 5 squared gives me 5 to the power of 3, which is really just 125. And then I have q4 p squared. So for our next exponent law in grade 10, we're going to take a look at powers with negative rational exponents. Now we've already covered both aspects previously. We've talked about what happens if we have something such as 16 to the power of -1. Well, this would just be 1 over 16 to the power of +1. Now we're going to combine that with the idea of having rational exponents. And we learned just now that 16 to the power of 1/2 is the same thing as the square root of 16. So all we're really doing is just combining these two aspects. And knowing that 16 to the power of -1 means we're going to end up putting it in the denominator. When we combine that with the idea of having a radical, 16 to the power of -1/2 is really just the same thing as 1 over 16 to the power of +1/2, which is 1 over the square root of 16. And then we can simplify that to 1 over 4. So in general, we can go ahead and say that a to the power of -1 over n is the same thing as 1 over a to the power of 1 over n, which is really the same thing as 1 over the nth root of a. So we can go ahead and try out a couple of examples. So this would leave us with 1 over 9 to the power of 1/2, which is the same thing as 1 over the square root of 9, and we can simplify this as 1 over 3. In example number 2, we can combine a couple of different exponent law rules. In example number 2, we can combine a couple of different exponent laws. Since I have a fraction inside of my brackets and a negative exponent, I'm going to go ahead and flip my numerator and my denominator and make that exponent a positive now. I'm going to distribute that 1/2 to both the 16 and the 9. So I have 16 to the power of 1/2 and then 9 to the power of 1/2. And we know that I have the square root of 16 over the square root of 9, which becomes 4 over 3. This last example, we're going to start off the exact same way. I'm going to flip my numerator and my denominator. I'm going to just keep the negative inside for now. It doesn't really matter what number the negative is on. And now it's going to be to the power of positive 1/3. Like I said, it doesn't really matter which number the negative is attached to, either the 27 or the 8, but not both. So let's go ahead and keep it attached to the top. So now I'm going to distribute that 1/3. So I have negative 27 to the power of 1/3 over 8 to the power of 1/3. So we're looking at the cube root of negative 27 over the cube root of 8. So this leaves me with negative 3 over positive 2. One way to check your answer is if you plug in your original expression into your calculator, it should match up with whatever you end up getting once you've simplified the expression. So this rule at the top here is exactly what we talked about much earlier in the video. A to the power of m over n is really the same thing as the nth root of a, and then in brackets, raised to the power of m. Alternatively, we can also write it as the nth root of a, but we attach this exponent on the inside underneath the radical. Honestly, I prefer that most students stick with this one. This is going to be much simpler to use compared to this one. We're going to take a look at some reasons why when we do some examples together. In the same vein, if we have a to the power of negative m over n, this is really the same thing as the nth root of a, and then with the brackets, raised to the power of m. So let's try a few questions without using a calculator. This 3 here tells me that my index of my radical is going to be a 3, and now my base is going to be an 8. And because I'm going to use this first version of this exponent law, I'm going to go ahead and put the brackets around, and I'm going to raise it to the power of 2. We know that the cube root of 8 is just 2. Raised to the power of 2 means that I have 4. Similarly, in my second example here, this 2 means I'm taking just a square root of my base, 25. And what I can do is I can either cube it on the inside or I can cube it on the outside. It's going to be much easier for us to cube it when it's on the outside because I know that the square root of 25 is 5. I'm going to have 5 cubed, which I know is 125. If we did it the other way and I went like this, the square root of 25 cubed, this would be the square root of 15,625. Now, of course, this would give us the exact same answer. However, this is a lot more difficult to do without a calculator compared to our first iteration. So once again, try to stick with having your brackets up and raising it to the power on the outside. So now go ahead and pause the video, try out the questions, and then unpause once you're finished. So taking a look at this question here, this is one of the ones where it gets quite tricky. I'm going to go ahead and draw my line for a fraction, and I'm going to think about what's actually happening here. 5 divided by 25 can simplify to 1 over 5. So I'm actually going to go ahead and write that here. 1 over 5, so that's what these two coefficients reduce to. 5 over 25 is 1 over 5. And now I can go ahead and work with the x's here. X to the power of 3 over 5 divided by x to the power of negative 3 over 5. I'm going to add them because when I subtract a negative, I am adding. So I have left with x to the power of 6 over 5. And I can just simplify this to x to the power of 6 over 5 divided by 5. I realized the last part of this video went ahead and skipped through a lot of the explanations, but I wanted to make sure that I kept this video under an hour long. If you have any questions, feel free to leave them in the comments below. I hope you guys found this video helpful. Thanks again for watching, and I'll see you guys in the next video.